And then on Wednesday, you'll actually use Cell Organizer hands-on. So today is mainly going to be how to build realistic models, spatially realistic 3D reaction diffusion models with the MCell tool, stochastic, particle-based stochastic simulations. And then tomorrow, you'll learn about Rule Bender and BioNetGen, which is, I think, a much more serious tool for the raw biochemistry of cells. And we're working hard to try to integrate some of the capabilities and the expressive capabilities of the BioNetGen language into Cell Blender for use in MCell. And in the afternoon tomorrow, we might get to that point, but tomorrow you'll be learning about all the expressive power of the BioNetGen language and the power of Rule Bender. And then on Wednesday, all about Cell Organizer and how to create generative models of cell structure for incorporating for the purpose of analysis of cell structure, but also for incorporating into realistic models of biochemistry in cells. So, to start with, if you've got, the first thing to do would be to open a terminal window, because some of the output from, even though we're going to be using Blender and Cell Blender, which is a graphical tool, some of the diagnostic output from those tools will appear in your terminal window. So the tools we're showing you here are tools that should run about the same regardless of what platform you're on. So it runs on Linux, it runs on a Mac, it'll run on Windows. Personally, we use mostly Linux and Mac OS X in our research group. We don't use Windows that much, so it might not be as well tested on the Windows platform, but that doesn't mean we don't intend it to work perfectly there. So, like I said earlier, one of the things we like to do is get feedback from you on what works and what doesn't, especially when it comes to problems on the different platforms. Okay, so if you've got a terminal window up, then to start up Blender, you should be able to type in the command Blender on your command line, and after you do, put an ampersand after it. And I'm going to type my Blender because I have a script that fires it up. And when you do, you'll get a splash screen that looks like this. All right. Which is the typical Blender splash screen. And we'll be covering as we go, bit by bit, some of the ins and outs of the Blender user interface, but we're not going to go into great depth into it. Blender is an incredibly powerful tool for making Hollywood-style computer graphics imagery. It's a complete, what they call a complete 3D content creation suite of tools. With Blender, you can integrate live action film footage with 3D computer graphic imagery, with 3D motion tracking of the motion of the camera, and with sound and special effects to create your own version of Jurassic Park if you want to. And there's lots of examples on the web of exactly this sort of thing, and they have lots of tutorials on the blender.org website for how to do all that kind of stuff. Here we're just going to barely scratch the surface of that kind of thing, but go into great depth into what we've been able to do with it to integrate it into our, as the front end to our 3D modeling capabilities. Okay, so along the, so you've got a 3-button mouse, and Blender really likes to have a 3-button mouse and a full keyboard with a numeric keypad on it. My Mac does not have, my MacBook Pro here does not have a numeric keypad or a 3-button mouse, but there's a way to set up the user interface so that you can use it for that. So if you've got a laptop like that, you can do it. No, but I'm happy. I can make it work like a 3-button mouse. So, and there's hotkeys for almost every function in Blender. Blender's used by 3D computer graphics artists every day for 8 hours a day or 12 hours a day to be very productive for them. So the user interface is very productive after you learn all the hotkeys. We're just gonna we're gonna be doing exercises that do lots of repetition, so you'll be able to learn by repetition all the things that you need to do.
Does the help menu have a good list of hotkeys that's easily accessible?
The help menu will take you to a website that has all the lists of all that stuff. Yeah, there's lots on the blender.org website. There's tutorials that start from the beginner level, and there's cheat sheets with what the hotkeys are. As we start using it, you'll notice that next to, for example, if I click on the File menu, you can see along the right-hand side of the menu what the hotkeys are for all those commands. So to begin with, as we start using the tool, I'll be using menus and then pointing out what the hotkeys are, and as we do more and more repetition, I'll say, now I'm hitting this hotkey to do it, right? So we'll kind of build up that way. So, okay. So to start with,
they need to initialize, because you're already initialized. They're seeing different screens than you are.
Ah. So I don't know what they're seeing.
They need to upgrade.
Ah, okay.
You'll be out of sync if you just
Okay.
launch it.
All right. So I'm going to click on the Cell Blender tab along the right-hand side. I mean left-hand side of the window is this bar called the toolbar. I can toggle the appearance and disappearance of the toolbar by hitting the T key with my mouse in the 3D view window. So if you put your mouse in the 3D view window and hit the T key on the keyboard, you should see the toolbar come and go. So, so that's called the tool shelf. And for me, in order to get my screen to look like yours, I'm going to click on a tab called the Cell Blender tab. And this is what I see when I do that. And then when I click on this, so you're going to have to say, in order for you to see this, you'll have to hit upgrade. The top. Yeah. Okay. And then then your screen should look like mine, except that your screen doesn't have any of this. So when Jacob set up these machines, he set it up so that he made a default view here that doesn't have any of the stuff in it. So that's why your screen looked different. So but if your screen comes up with all these gadgets in it when you're going to build a new model, so this is the default Blender screen when you start Blender from factory default settings. It comes up with a cube, which is like your lump of clay if you're an artist, that is ready for you to beat on into whatever shape you want. This is called the camera, and then there's a lamp that lights up your scene. So that's kind of like the most basic scene for 3D computer graphics that you'd want to do. But we don't need any of that. So I'm going to use the A key to select everything, and then I'll hit X to delete it, and then it's gone. So now my screen looks like your screen. Okay. So so now what I'm going to do is with my left mouse button, if I click, you'll see this little this little bug run around. I'm calling it a bug because if you're in a heads-up display on an aircraft with a heads-up display, you'll have this little thing called a bug. Well, that's the bug. So to put that thing back to dead center, there's a hotkey called Shift S, which is the snap hotkey, and I can snap cursor to center. Okay, that puts it back to the center. So the left mouse button is normally used by graphic artists to change the locations of vertices and tweak vertices. You don't want to do any of that. So we're going to be using the right mouse button to select objects. So don't use the left mouse button for any of that. We're going to use the right mouse button when we get to that point. Okay, so to start with, we're going to make our first model for running an MCell using Cell Blender. And to do that, we're going to create a molecule. So click on the Molecules tab. Which is right here. So this is the basic interface for Cell Blender, and at the button across the top contains a bunch of example models that you could load and play with. But we're going to make our first model from scratch. And every model of reaction diffusion starts with the molecules. So if you click on the Molecules button, then you get the Molecules tab. And if I hit the plus button, so you see a list here of the defined molecules. There aren't any. If I hover over any of the buttons here, I get some help, some bubble help that pops up. The plus button says add a new molecule type to an MCell model. So I'm going to click on the plus button. And by default, the molecule comes up named Molecule 1. But I'm going to change its name. So I'm going to click on the name of it below the panel. And what the model that we're going to create here is a 3D reaction diffusion model version of the Latko-Volterra predator-prey interaction model. And you may have heard of this model or played with this model in biochemistry classes or learned about it in dynamical systems classes. It's a classic model, but I doubt you've ever seen anything like we're about to do with it. Because though the classic analysis of that model is from the point of view of a point process dynamical system of ordinary differential equations. And the twist on it here is that we're going to have the predator and prey be particles that are spatially distributed, and they encounter, and in order for them to encounter each other, they have to diffuse and contact each other, as predator and prey often do, right? And so you're going to see some really, really interesting things here. So, but first we're going to start with our molecule, and we're going to start with the predators. So change the name of the molecule to predator. And in the MCell world, we have two kinds of molecules. We have volume molecules and surface molecules. These are going to be volume molecules. And that's the default. And we're going to give a diffusion constant to our predators. And our diffusion constant, I can't remember what the diffusion constant should be. Is it, I have a cheat sheet. And I'm usually not quite this disorganized, but coming in at 2:30 in the morning last night has got me off sorts a little bit. I'm going to put in 6e minus 6. Or I can cheat and peek. at another version of the model. I'm gonna cheat and peek. So I've opened another Blender, and I'm gonna cheat and peek at it. Yeah, 6e minus 6. Everything else I know. All right. Okay. And so that's our predator molecules. And then we have to put them in the world. So we're going to build this model up piece by piece so that you can see all the elements of what a 3D reaction diffusion system is made of. A particle-based 3D reaction diffusion system. So we're going to start with a single particle of predators. So under molecule placement, we're going to add a molecule placement site. So you can see our user interface is constructed of elements that kind of look and feel the same, so that there's not a lot of surprises. So I'm going to hit plus to add a new release site to the model, and we're just going to leave its name at release site 1. But for the molecule to release, well, there's only one choice, the predator. So if I click on molecule, I'll get a drop-down menu that shows me the choices. And we're going to start with releasing them in what's called a spherical release site shape. There's a number of choices for release site shapes, and we'll be doing more of those later. But we're going to start with spherical, which is a spherical distribution of uniformly distributed particles. But we're going to put them at a location 0, 0, 0, and with a diameter of their spread of 0. So that makes it a point release, right? There's lots of choices for initial distributions of particles in the tool. Release probability is 1, which means at t0, at time 0 at the beginning of the simulation, there'll be a probability of 1 of releasing our particles, and we're going to release 1,000 of them. And when we release particles, we can release a constant number, or we can release a Gaussian distributed number, which will vary from one trial to the next with a certain mean and standard deviation. Or I can release a concentration or density, but that only makes sense if I have a volume to distribute them over. And this is going to be a point release into infinite space, so the whole concept of concentration doesn't make any sense. So obviously, constant number is what we want. And then there's an option for a release pattern, which is like a stimulus generator kind of waveform of pulses with time delays and train durations and number of spikes per train kind of concept, but we're not going to do that here. So your setup should be, we're going to release molecule predator in a spherical release site with location 0, 0, 0, diameter 0, probability 1, constant number 1,000. Okay? And now, if you go under Run Simulation, the default number of iterations and time step appear. And let's set our time step to 1e minus 8, which is not the default, but we'll be using it. We'll need that for later. And we'd be ready to run, except that we haven't saved our file for the first time, and it's reminding us that we need to open or save a blend file in order to set up the project directory, which is where all the files are going to go when you do a run. Okay? So to do that, I'm going to hit Control S, or you can say File Save, but the hotkey is Control S or Command S, and then a file navigation window will appear, and Usually what you do is I've already got this set up to go in a certain location. I'm going to navigate to my home directory. So because this will be more like what you see, you probably see your home directory. And if you, I'm going to make a new directory called CMW for Cell Modeling Workshop 2017. And if I put that on the top bar, which is where the menu goes, I'll say create new directory. And then for the file name, I'm just going to call this LV Diffusion Limited. So in the classic version of the Laca-Volterra reaction, there is since it's usually done as an ordinary differential equation, there's really no diffusion usually treated in that dynamical system. So the concept of whether it's reaction limited or diffusion limited doesn't come into play because there's usually no diffusion. So you get this oscillation of predator and prey in boom and bust cycles. But here, since we have a reaction diffusion system, we can play it in two different ways. We're going to start with the diffusion limited way to do it, which is the new concept that you're gonna see. So that's why I'm calling it diffusion limited. I say save my blend file. And now under run simulation, now a new button appears saying export and run. So if I click on export and run, mine ran really fast. You get a little pop-up. You get a little menu that a list that appears that shows the process ID of the run and what random number seed was used to do the run, and as it runs, you get progress.
I think I have that.
Uh-oh.
Already.
They need to save someplace else. A lot of them are getting permission errors.
Well, yeah,
Oh.
it looks like by default, it's probably because of how the two IP machines are set up, that you want to make sure
Oh.
somewhere relative to your home directory. I think it's throwing them directly in /home.
So I
Oh,
can
oh, oh.
Yeah.
Oh,
so
oh.
It should be,
So
it shouldn't be like /home, it should be home/user too.
Okay.
So,
User two?
Can you go to
Yeah.
file
How
save?
do you know that's me?
Yeah.
Because I saw it before.
So-
0, 1, 2.
Or file save as.
So
Yeah.
So you should all see some bookmarks here. And I think everybody should have a bookmark that probably actually will say like user 0, 1, 2, 3, 4, something like that. Click on that one. That will put you in your home directory then. So
Okay.
anywhere in there you should have permission to write.
From 0.
It's just you were, you know.
Yeah.
Well, if you're just in /home, that's like, one level up.
Yeah,
from where you
okay.
should be.
Okay.
It'll be diffusion.
Yeah, so anywhere.
So navigate to your actual home directory.
Yeah, all the /home/user.
So in the system,
System bookmarks.
in the system bookmarks area, look for one of these that has your username in there,
But the name will be what kind of name?
like user 1, user 2.
Username should be something like /home/user 0, 1, 2, 3 to 7. So
Is it /home?
this
0?
row should be like 0 to 7, and then this row will have another 6 that is 0 to 7. And you'll just see it in the system bookmarks where Tom was in file save as on that left hand side. You should be able to see over there.
So has everyone been able to save successfully?
Yeah.
Yeah. Okay. So then after that, you should be able to hit run. So I'm going to, after your run is completed, if you want to run it again, I can say clear completed runs and then say export and run it, just so you can see, run it again.
Okay. So
You just the same thing
It-
one every time.
Yeah. Okay, so after your run is completed, in order to see the result, you'll need to hit reload visualization data, which is this button in the lower right-hand corner of the control tabs.
So I hit it, and then it...
Okay, and so since we were with a new simulation that you've just run, it starts you. It shows you the state at time 0, or wherever you last left the model if it was previously saved. But this is our brand new model, and so the points, all the particles are at a point in the middle of the world, and we can't really see them. So let's hit at the bottom of the screen is the time bar that has some VCR control, VCR looking or DVD control looking buttons, or movie playback control looking buttons. I would date myself saying VCR, I guess. Yeah. So hit the play button, and if you look, you'll start to see something's happening in the middle there. And so to zoom in, so I'm going to hit pause. I'm going to hit the pause button to pause it there for a moment. So to zoom in, you can use the middle scroll wheel on your mouse. On my Mac, with a touchpad, I can just use my pinch motion and zoom in. There they are. And I've zoomed in quite a bit. And I'm at hit the play button, so I'm going to hit the play button again. And I can see the particles going. I'm going to go back to time 0 by hitting the leftmost rewind button, which looks like double rewind with a stop. So that rewinds back to t0. So now I see my one particle, or all the particles at a point. It's actually 1,000 particles at a single point. And now I hit play, and this is what I see. And if I middle click and drag, I can rotate.
Middle click of the roller wheel?
Yeah. Because the roller wheel is also a middle mouse button.
Yeah.
Right? So if you middle click and drag, you can rotate the scene. And middle click and middle scroll, the scroll wheel, without clicking, will let you zoom in and out. Let's see. And if you hit Shift, middle click, and drag,
Yeah, translation.
which that'll do a kind of a panning motion or a translation motion.
When it's a rotation, isn't it?
And if I accidentally lose the world, right, you can hit the C button. I'm sorry, not the C button. If you accidentally hit the wrong thing, I hit the C button and I get this like a circle select tool. I'll hit escape to do that. I think you hit Shift C. Shift C will recenter the view on the origin.
Oh, three. Oh, no, yeah, go to the next one.
Okay.
So when I had C up, I had Control C, Shift C something, and then I click. Now I have a little red dot in the middle. How do I get rid of that?
Hit play, and that red dot is your particles.
No, it's a new red dot. Came directly from, I had the circle from the Shift C, and then I
Uh-oh.
clicked.
What do you mean? It's not the bug thing.
See this little dot?
Oh, yeah, that's the 3D cursor. That's called the 3D cursor.
Oh,
Yeah, now you have it over there.
No, this thing. How do I get rid of it?
Oh, the orange thing. You can't get rid of that. It's
Why not?
basically a dot that shows you the center of your molecule prototype, but don't worry.
Huh.
And it's not there.
And I don't know.
It's
Okay.
An object origin, every object has its own origin, just like the world has an origin, so its own objects. Yes. Well, it's orange when it's selected.
It's an origin.
But it only showed up when I.
Because it was selected.
Okay, so I'm going to hit pause and then rewind back to time 0 again, and then hit play, and you'll notice if you've got if you were zoomed out, well, if I go to time 1000, so I'm going to hit actually fast forward all the way to the end. So that's the rightmost fast forward button, which will take me all the way to time 1000, right? Because we ran for 1,000 iterations. And my world looks like this. So if I kind of scale my view so that kind of fills the view like this, and now rewind and now hit play, you'll notice that initially there's like a rapid expansion of the universe, kind of like inflation of the universe, which was fast at first. And then it seems like it's just kind of stuck there, and it's not spreading very fast anymore. What's up with that?
Concentration-dependent diffusion.
Right. So this is the diffusion equation that says that the rate of diffusion is a function of the gradient, of the concentration gradient, right? And that sounds like.
That sounds reasonable for Bredesen as well.
Yeah, that's the right answer for Brownian motion of diffusion in water, right? That's the right answer, but it sounds like that means that diffusion is concentration dependent, but it's not. It's only dependent on the gradient of the concentration gradient, right? And that sounds like there's a force that's pushing the particles apart. And that force gets less and less the farther apart the particles are from each other. That's BS. That's what the math says. But that's not physically what's happening. The particles don't repel each other. The reason why that equation is the equation that describes this motion it has to do with the probability distribution of the particles. The gradient is really about the probability distribution of the position of the particles. Outside this bubble, there are no particles. Inside this bubble, there's a lot of particles. The particles are doing a random walk. A single particle doesn't know about any of the other particles. It's just doing a random walk. And all the particles are doing the same random walk. And there aren't any particles out here to take the place of any particles that move outward. There's no particle out here that can move inward to take its place. So that's why it's spreading out. It's because the probability that a particle moves from outside to in is 0 out here. And there's a lot of particles in here that are doing random walks. And if any of them walk outward, they walk outward.
So every time one moves outward, it shifts the probability distribution and makes it more likely another one moves outward.
That's right. That's what random walk is. That's what diffusion is. It's about increase in entropy, increase in disorder, right?
Yeah.
It's highly unlikely that there should be no particles out here if particles can move to get out there. So this distribution is a highly unlikely distribution. So as time goes on, it'll tend to spread out so that there's an equal probability of the particles being everywhere. That's the maximum entropy, maximum disorder. But the individual particles don't know about each other. There is no force that pushes them apart. So that equation is the right equation, but if you look at it the wrong way, it looks like there's something that's pushing them apart. And it ain't so. Okay. So now we're going to move on to the next step.
So the particles can, if they're not aware of each other, there's no exclusion point. They can move through each other.
Right. Okay. So So now we're going, if anyone would like to see more information about diffusion theory, we have slides that I could go into on that, but that little snippet there was my brief teachable moment on diffusion. And there's an analytic solution to the diffusion equation in this case of particles moving in unbounded space, unbounded three-dimensional space. There's an analytic solution to this problem, and what MCell is doing is applying that analytic solution to the motion of each particle individually and computing it numerically so that we have the random walk of every particle. Okay? Okay, so now we're going to add a reaction. So the most basic thing for reaction diffusion is to have diffusion of our particles and then reaction, right? So we're going to add a reaction. So click on the Reactions tab, and we're going to add a new reaction by hitting plus. And the reaction we're going to apply is predator. And there's two kinds of reactions. We can have an irreversible reaction or a reversible reaction, right? So this is going to be an irreversible reaction. And the product of the reaction is null, in all caps, N-U-L-L.
Then the predator can disappear.
Right. So this is, so the predators disappear because they die. And if they have nothing to eat, they die. And right now, there's nothing for them to eat. And so we put in the equation for predator death. And the death rate let's see, is going to be 5 million per second, 5e6. So they don't live very long, these predators. And this is the classic equation for annihilation in reaction diffusion theory, or in reaction theory. It's just called annihilation. So I said that there's an analytic solution to random walk in infinite space from a point source. And also there is an analytic solution to annihilation, also called decay or radioactive decay. Right? It's an exponential decay function with a time constant, an exponential decay time constant equal to the 1 over the time 1 over the rate, or so 5 million per second. So the tau is 1/5 millionth of a second, right? But if you put reaction and diffusion together with this. With these two simple equations that both have a separate analytic solution, you get a system for which there is no analytic solution to what's the distribution in space and time for particles that diffuse with a random walk and decay as they go. There is no analytic solution to that very simple system, but of course there's a numeric solution, and we can compute it with this. You get a function in space and time that has a shape, but there's no analytic equation for the shape of that waveform. Okay, so now under Run Simulation, I'm going to clear out my completed runs. I'm going to hit Export and Run, and boom, it ran that fast. If I hit Reload, I stop. My simulation was paused in the middle of somewhere. I see nothing, so I'm going to go back to time 0.
Wait, did you name it? Reaction name?
Oh, no, I didn't. Don't name your reaction.
Okay.
So I said predator goes to null, forward rate constant 5e6. And it's an irreversible reaction. Yeah? Okay.
And then quite quickly they're over.
Okay.
Oh,
Is it working?
I guess
No,
now it says undefined molecule printer, which is next up.
go back to your monitor. Oh, you've got a capital T.
Oh, that's
Yeah, it's case sensitive. The names of things are case sensitive.
Or you can bring it
all right.
Okay.
So you're saying the keyword null has to be all caps?
Yeah, and the keyword null has to be in all caps. N-U-L-L.
Nice.
Got it? Okay. So when I hit play, I see the particles spreading, and then they die out. Well, that's not fun.
Yeah, can we get some spray up in here?
Okay. So now we're so let's see how long those guys live, right? So let's go into the plot output settings. So click on the plot output settings button, and we're going to add some plot output. So the default settings for step and output buff size are okay. There's no default, or default for that is empty. So I'm going to click plus to add a new plot. Yeah.
I don't know how the MATLAB plotter stopped working, but they have the XM Grace one. So
Okay.
just have them use that.
Okay. Okay. And we're going to add an output for counting molecules. So we're going to count the predators in the world. And I'm going to drag this down so I can see more. So there's since I have limited real estate, this thing at the bottom is taking up a lot of space. So I'm just going to I clicked on the border between it and then dragged it down so that you can see what I see. Okay. And now I have, in order to see my output, I have to run again since I've just added new output. So I'm going to clear my runs. I'm going to say export and run. Runs again.
How did we add it
Oh,
out?
so to add an output, click on the plot output settings button, and then hit plus to add a new output. And then by default, it's set up for molecule, but I have to choose the molecule predator, right? And then click on world. And now that since I've done that, I have to run again to generate it, because my previous run didn't do that.
Yeah.
And then back over here, now I can hit plot. But the default setting to matplotlib plotter for you, so for some reason it's broken at the moment. So you're going to use the XM Grace plotter instead,
Yeah, running.
and hit. And then after you run again and choose XM Grace plotter, I can hit plot,
Yeah.
and then I get the graph that shows the predators dying out very quickly. Okay. Then I can hit exit to quit from that, and now we're ready to do our next thing. So let's add some prey.
Where's plot?
Go down.
Okay, so under molecules, I'm going to add a new molecule, which are going to be the prey. I'm going to change their name to prey. And it's a volume molecule, and the diffusion constant is 6e minus 6 again. And to put them in the world, I have to say molecule placement. And I'm going to put them in the world. I'm under a new release site. So I'm going to hit plus to add a new release site. And for some reason, mine says it's a duplicate release site name. I'm not sure why. So I'm going to change its name to release site 2. And I'm going to choose pray. And again, it's going to be a spherical release site from 000, constant number 1,000. And now if I run, I'm not going to add any reactions yet. Now if I clear my runs and I say export and run, now it ran. And now I can see the prey running around, and the predators have already died out because they're not eating any of the prey yet because we didn't tell it to do that. I'm going to add a plot output for counting the prey, which I didn't do a second ago. And I'm going to run again. And now since I've ran, I can plot. So I added a release site of 1,000 prey. And so now I can see my prey up here. I've got 1,000 of those, and my predators are dying out. Okay? So next, we're going to add the predation. We're going to add the predation reaction. So click on the reaction tab and add a new reaction. And this reaction is going to be predator plus prey. Goes irreversibly to predator plus predator. So it should be predator plus prey goes to predator plus predator. So this is going to, so the predators are going to be eating the prey and reproducing and making new predators. But eventually, of course, they're going to run out of prey.
Yeah.
But don't worry about that yet. That's what we're going to do. And the rate at which they're going to eat the predator is 1e12.
Should they not maybe be reproducing anyway?
No, they can only reproduce if they eat a prey.
But the prey can reproduce anyway.
But we're going to do that in a minute. We're building this up step by step. Okay, so now I can hit run simulation.
How many predator and prey did you release?
1,000.
1,000 each?
1,000 each. Okay, and so now if I hit reload the visualization and hit play, what happened?
They got immediately eaten.
They got immediately eaten because they were released from a point source. And so they were immediately on top of each other, and the predators were able to eat the prey in one time step.
Okay,
So if we look at our graph,
How do we switch to access on our plot?
I think he's...
Oh, it throws that. Okay. This is total particles then?
yeah. Why is that showing like that? Oh, I'm sorry. Now, notice the time scale on the... No? Why is I'm confused.
So the prey goes down immediately, and the predator still decays, but maybe closer.
Not,
Immediately, them
oh.
2000, and then
Oh, there they go. All right. I was looking at the wrong time. Yeah. So it's doing the right thing. I was looking at the wrong time. So the prey are gone instantly, and what's left are the predators. And yeah, if we look, so go back to my plot. Oh, if you look at the initial total, right? We released 1,000, but it very quickly shot up to a very high number, and then it decays away, right? Yeah. Okay, I was confused. It's good to be confused, and so.
I'm seeing different pictures on some of these screens. So
Ah.
it might be going a little bit fast.
Okay.
Somehow I lost all the reactions.
Okay. Okay, so to review, we have two molecules, predator and prey. They're both volume molecules, and they both have the same diffusion constant of 6e minus 6. Okay. And for the reactions, we have predator goes to null with rate 5e6. And then another reaction called predator plus prey goes irreversibly to predator plus predator. And the rate of that is 1e12.
What are the two rates?
5e6 for the annihilation of for the death of predator. (5e6) 5 million per second. And the next reaction is predator plus prey for the reactants. And the products are predator plus predator. And the rate constant is 1e12. Those are the two reactions. Okay. And we're releasing both of these from point sources. If we're all on the same page, next thing we're going to do is we're going to go back to our molecule placement, and instead of releasing from a point source, we're going to put in a diameter for both. For release site 1, we're going to release them from a diameter of 0.1. We're going to make a diameter of 0.1
For both predator?
for both. And the units are in microns.
The default?
No, it's not. The default is 0, I think. Oh. Yeah. So the units here are arbitrary units, right? In Blender, Blender is mostly in arbitrary units. So the units mean whatever you want them to mean. In this case, the meaning is interpreted by MCell, and in MCell 1 is 1 micron. 1.0 is 1 micron, right? And MCell's time unit is seconds. And concentrations are moles per liter, not micromoles. So if you put in 1 for a concentration, it'll be a lot. Right? Okay. So now I've set the site diameter of our spherical release site for release site 1 and 2 to be 0.1 microns. That's 100 nanometers. Right? And if I hit now I'm going to hit run again. So I'm going to clear out my completed runs and hit run again. And now if I hit go, now it's a little bit more interesting. For me, 2 of them got away.
Yeah, same.
And it should look like amazingly exactly like what I see, because we're all running the same version of MCell. We're all running with seed number 1. You'll get a different result if you run with a different seed, but let's just stick with seed number 1.
Can we make it a right
And if I go to my plot output and now look at my plot output, the predators aren't quite as successful. The peak number they get to isn't quite as high as it was before, but they still die out. And the surviving, way down here in the corner, is the survival of the prey. And if you're using the XM Grace plotter, if you click on the magnifying glass button, it'll let you draw a rectangle. So I'm going to draw a rectangle, I don't know, around the corner down here. And then this is showing me what the predators are, what the prey are doing. They very quickly decay down to nothing, but they survive a little bit longer than they did before.
How do we get the right thing?
And then to go back to the default view, this button that says AS in it is the auto scale button, and that takes us back to an auto scale view. Okay, but that's enough plotting. Okay, so now we've got predator and prey, and with the setup we have now, if we were to add the reaction, the scary reaction, which is why we left it to be the last thing here. The scary reaction is the prey reproduction reaction. These prey are very prolific and promiscuous.
Should they not also have a lifespan as well?
We don't give them a lifespan. They can live forever. In the classic predator prey, in the minimal version of Laca Volterra, the prey never die. They have to be eaten in order to be killed, right? If we were to do that right now with this setup, these 2 survivors would reproduce to take over the whole universe. And if you're doing an ODE simulation of this, it's just a number that blows up to infinity. In our particle-based simulation, it turns out to be an infinite number of particles, which would take up all the RAM of your computer in no time at all. So we have to be very careful with the particle-based reaction diffusion version of this model. So to give the predators more of a chance,
We could say to make the prey only reproduce if they collide with each other.
we could do that, and then but we haven't. This would be left as an exercise for you guys to play with. For the lesson today, what we're going to do next, before we let's see what's going on here with my. Why isn't that? Okay, I'm having trouble. There we go. What we're going to do next is we're going to make a box that's going to contain everything, so that we have containment of the prey. Mainly this is so that we have containment of the prey, so that they can't get away from the predators as easily and then reproduce without bounds. So to do that, we're going to click on the Model Objects panel, or button, and we get this control panel. And in this control panel, across the top are a number of built-in canned kinds of geometries. And so I'm going to, and in Blender, geometries are always created at the location of the 3D cursor. So remember that if I click with the left mouse button in the 3D view window, I can put the cursor wherever I want. But we want our box to be at the origin, so we've added a convenient button here that's a shortcut to the center of the cursor button. And it's this second of these two leftmost buttons. And it says snap the 3D cursor to the center. So make sure you do that first. And then a little bit over to the right of that, the very first object button is construct a cube mesh. So click on that, and we get a cube. And if I zoom out, I can see my cube, and with my middle mouse button, I can click and drag and rotate this cube, and we can look at it from every angle. We're going to want to set the size of this cube. So the convenient way to set the size of this cube is to use another control panel called the numeric control panel. And to get it, if you put your mouse in the 3D view window and hit the N key, N as in Nancy, then on the right-hand side of your 3D view window, another panel appears. This is the numeric control panel. And I'm going to set the dimensions of the cube. So by default, the cube comes up 2 by 2 by 2. That would be microns, right? So we're going to set the size of our cube to be 0.5 in X, 0.5 in Y, and 0.01 in height. That's going to make a little slab, which now I can zoom in on and I can see it. I can look at it from all angles. And right now the box is opaque. There's a number of different view options for looking at this. Okay, but we've now set the dimensions of our box, and now what we need to do is to add it to our MCell world as a model object. Okay, so the Blender. So the way we've constructed this tool is to make it easy for you to make your model, of course, but also make it easy for you to make the scene look the way you want and annotate it with annotations, so you get a powerful and effective visualization for yourself, and also for making presentations. And in 3D scientific visualization, it's often the case that you'll want to include in your scene that you're showing viewers extraneous or ancillary objects that are there just for just to orient the viewer as to the scale or size, or with other annotations, things that might not be officially part of your model, right? So we kind of split concepts here. We have a concept of a scene which can have anything in it, and then within that we have a concept of items that are in your scene that are also part of your MCell model. Okay, and we call these things that are part of your MCell model, we call them model objects. So you can have lots of things visible in your scene that are not part of your model object. Okay, so right now I've got the cube selected. At this point, we can experiment with a key in the 3D view window, which toggles selection of objects. Right. So if I hit the A key with my mouse hovering in the 3D view window, if I hit the A key, that toggles selection and deselection of objects in the scene. And you'll see that the cube gets highlighted. And if we were to zoom in on our molecules, we would also see that the molecules might get, oh, well, no, they don't. They don't get highlighted. And that's because by default, when Cell Blender imports the molecules from your 3D visualization, they get set to be unselectable. so that you can't accidentally click on them and mess with them, okay? But the other way to select an object is to right-click on the object. With your right mouse button, point at your object, and then click on it with the right mouse button, and then it will select the object. And if you notice in the lower left-hand corner of your 3D view window, you'll see the name of the cube gets listed there. That tells you the name of the object that's the current active object. You can select more than one object at a time if you want to, but the name of the last object that you clicked on becomes not only a selected object but also the active object, and its name, the name of the active object, will be listed down here. Okay. So now, but to verify that we have only one object selected, if you go to the top menu bar of the Blender window, over to the right, you'll notice some information about our object. We have 94 vertices, 156 faces, 172 triangles, and I've got 6 objects. That would include the molecules and some other things. But it says objects 1/6. That means I've got one object selected out of 6 total objects. So oftentimes you want to make sure that I'm about to do something. Do I really have only one object selected? Sometimes it can be hard to tell. You can look up here and say, yeah, one object selected, 1 of 6 in my case.
Your simulation's at a different point.
Your simulation might be at a different point, so you have different numbers of molecules present, possibly.
It's just not telling me the number of objects. It's telling me what these edges, faces, and things.
Oh, you must have accidentally hit the Tab key. So, so if you go down, another important thing there's a lot of keys on the keyboard. It can be very overwhelming, right? If you go down to the bottom of the 3D view window, over about a third of the way from the left, you'll see a drop-down menu, and that has a bunch of different modes for the 3D view window, and you should be in object mode. So object mode lets you manipulate each individual object in your scene, and edit mode lets you edit a single object and change its vertices, edges, and faces and play with it like a piece of clay. But we don't want to do that, right? So make sure you're in object mode. And if your mouse button is in the 3D view window, if your mouse cursor is in the 3D view window, you can toggle between object mode and edit mode by hitting the Tab key. And then your view will change like you see here.
Yeah.
Okay. Make sure you're in object mode. And then you'll see you have one object selected.
I have 3.
Okay. You have 3 objects selected?
Yeah.
Oh, well, so hit the A key to toggle, unselect everything. If it doesn't say 1,
Oh, and then I can right-click.
and then you can right-click on just the one you want.
Yeah.
Okay. And its name will appear down here. It should say cube.
Mm-hmm.
Okay. So with the cube selected, go over to the Model Objects panel and hit the plus button. Hover over that. It says Include Object Selected in as a model object, right? Click on that. And then we see the name cube appear here. And under the cube options, below that, there'll be a little window that's expandable and hideable by clicking on the little triangle. And if you expand it, you get options for changing the view options, or the visual, the kind of the visibility options of this object. So for now, for cubes, what's really nice to do is if you've got something that's a rectangular cuboid kind of object, choosing wire. If I choose wire, then I see the edges of the triangles of it, and that's kind of ugly. Another option is bounds. And then you get kind of an outline of it. And since this thing is itself its own bounds, its own rectilinear bounds, then what you see is actually a representation of our object. And that's, for certain objects, this is a very effective way to look at it, and for this particular object. So do that, and now we're looking at it from the side. But what we have here is kind of an arena within which all kinds of drama is going to take place. And the best view is the aerial view looking straight down on it. And so if you go to the bottom of the 3D view window all the way over to the left-hand side, there's a menu called View. And what you want to say is View Top. So this gives us the bird's eye webcam view looking straight down onto our arena. And then you can zoom in on it to kind of have it fill as much of the screen as you'd like.
There's two view menus.
Yeah. So this is the view menu that's at the bottom of the 3D view window. If you go all the way to the very bottom of your whole screen, there's another view menu, and that's the view menu for the timeline. Right? So don't click on that one. Okay. So there's a lot of stuff in the Blender user interface here that you're learning. So throughout the hands-on tutorial, we're going to do a lot of repetition. So slowly, you'll start to get more adept with the tool and learn what to look at and what not to look at, and what not to click on. And then over time, you'll learn how to click on more and more things and what they do. OK, so with our top view looking down, we now have our cube, and we've added it to our MCell model, our Cell Blender MCell model, as a model object called cube. OK, and that's a perfectly fine name for the object, so we'll just leave it alone. OK, so our next thing to do is to change our molecule placement setting for, let's start with release site 1, which is for the predators. And instead of releasing them from a spherical point, we're going to change from spherical to object region. So our release shape is now an object/region. And the region, the object, and the name of the object/region is going to be cube. So type in the name of the cube. And release probability 1, constant number 1,000. So now, instead of releasing from a spherical release site with some user-defined diameter, we're going to release inside of an object.
Will it still diffuse out of the cube then?
No,
Oh.
it will not. So by default, the walls of the cube are going to be reflective to the diffusive motion of the particles. So the particles are going to be doing a random walk, but when they hit one of the, and these are what we call volume molecules, right? So these are molecules that do 3D diffusion, 3D random walk. We have two kinds of molecules that we can make in MCell, volume and surface. These are volume molecules. So in the context of volume molecules, when I say release on a certain object, that means in the interior of the object, right? So the object has to be fully closed. It needs to be what's called a fully closed 3D manifold, right? In 3D geometry, topology, jargon, these things are called, it's actually called a 2D manifold embedded in 3 dimensions, right? It's a 2D surface, but it's embedded in 3 dimensions. And what makes it a manifold is every edge between polygons is shared by exactly 2 polygons, not more, not less. And if you have an object that satisfies those properties, that every edge, every triangle edge, is shared by exactly 2 polygons, you get a closed manifold. The next criterion that has to be satisfied is the normals of the surfaces of each triangle has to point in a consistent direction, in this case outward. If the normals of the surfaces all point outward, then there's a well-defined interior and exterior of the object. The way the surface normal is defined is if you take the 3 vertices that make up a triangle, they're connected together in a certain order, 0 to 1, 1 to 2. If I take my fingers of my right hand and wrap them in the direction that the vertices are connected, my thumb will point in the direction of the normal. That's how we define the surface normal, okay? Typical right-hand rule in physics, okay? That's enough about that. But these are all the technical details. That's what the little teachable moment, another little teachable moment. You know, these are some of the technical details that go on behind the scenes to make this. But some of these things you have to know about. When things go wrong, you have to know, why did it go wrong? Oh, it's because of this, that, or the other thing. So we have a tool built in here that I'll show you, maybe take you quick to show you right now, that helps you know whether you've got an object that is suitable for counting on. So above your Cell Blender tab, there's a couple other little tabs with triangle buttons that open them up. There's one called Mesh Analysis. And we have our 1 cube object still selected. If I click on Analyze Mesh, it tells us that the object name is cube. It has 8 vertices, 18 edges, 12 faces. It's got 12 faces because each face is a triangle, not a square. And if the object were not triangulated, you would get a warning here saying object not triangulated. And there's a tool in Blender that lets you triangulate it. We'll see some of that later. Surface area to volume ratio, but mesh topology, it says it's watertight. That means it doesn't have any cracks or holes in it. And it's a manifold. And it has outward-facing normals. It's made of 1 component, and its genus is 0. Genus 0 means it's isomorphic to a sphere. It's not if I had a donut, it would still be watertight, manifold, outward-facing normals, 1 component, but it would have a handle. It would have a handle, something that a sphere doesn't have. The number of handles is the genus of the object.
So you don't need outward-facing normals to have a manifold.
You don't. Yeah. You could have inward-facing normals, but then the interior of an object with inward-facing normals, the interior of it is everything outside. That's its interior, right?
You can't have both, I guess.
You can't, right? You can't. And if the normals were inconsistent, it would tell you. It would say inconsistent normals. It would still be manifold,
Yeah, you still have manifold.
but it would say inconsistent normals. Yeah. So you get all the analysis you need here in order to know whether this is an object that I can use as a container, right? Yeah. Okay, that's enough about that.
So you have 2 objects, so you have one of them is inward facing, one of them is outward facing, and then you could use the face in between.
You could. So MCell doesn't care whether the normals are consistent, whether it's manifold, whether their normals are inward or outward, whether they intersect with each other. MCell itself doesn't care. MCell will model the reaction diffusion on that in the way that you expect. But what you can't do with it is count how many stuff is inside. And I can't release inside because there is no well-defined inside or outside. Mm-hmm. So but at runtime, MCell doesn't care. So if I have another way of getting my particles into that geometry that doesn't require that I know where inside and outside is, like I use a spherical release and put a point somewhere in space that I know is where I want it to be, you can do that, and MCell will simulate consistently after that point, right? But in order to do these easy, convenient ways of initializing your thing that says, I know this is a fully closed object with outward-facing normals, so I can release inside of it, and I can count how many molecules are in there at runtime because there's a well-defined inside, and I can tell MCell to count how many particles are in there. I have to have objects that satisfies these criteria. Okay, enough about that. Okay, so for release site 1, we're releasing in the cube, and we're saying constant number 1,000. Let's just leave it like that, and do the same thing for release site 2. Say we're going to release in the object shape of cube, constant number 1,000. Okay. And now's a good time to save again, because we've been making all kinds of changes. So the hotkey is Control S, or you can go to File, Save. And so now, before we add the last dangerous reaction, let's go to Run Simulation again. And I'm going to clear my completed runs, and I'm going to say Export and Run. And boom, it ran. And if I reload my viz, I now have, if I go back to time 0, I now see this. I see a uniform distribution of particles inside the box at t0. And when I run it, we have predators meeting prey and eating them, but the predators die out because they can't get to enough predators to reproduce very much. And then we have some prey that survive. But they survived a lot longer, and if I go to my plot output and hit plot, now I see this, right? So we have predator increasing to 1,300 or so, and then dying out, and then the prey surviving for much longer than they did before, and then their surviving number at the end is much larger than we had. Okay? So now we're ready for the last reaction. So under Reactions, add a new reaction, and this is going to be prey goes to prey plus prey. So they undergo asexual reproduction, I guess we could call it. So there, you can see there's a lot of variants of this that you could do. That would be a lot of fun. But the reactions that I'm showing you that we're putting in here are the classic reactions for the classic Lotka-Volterra. And now the rate of reproduction is going to be 8.6 E6. So be very careful to type it in exactly as specified. So we're just going to review the reactions one more time to make absolutely sure that everyone has the right values, because this is explosive, what's going to happen. So if some of you have simulations that blow up, there'll be a way to kill it, and we'll inspect and find out why. So make sure first of all, make sure I want to make sure that no one has changed their seed values. I didn't show you how yet, but you may have poked around and found. Make sure your seed value is set to 1. Oh, so don't worry about it. It's already set. It's set to 1 by default. Okay, so let's review. So the predator to null is 5E6. Predator plus prey. The predation reaction is 1E12. and then prey goes to prey plus prey. That's an irreversible reaction, and the rate is 8.6 E6. Yes? Okay. And you're releasing 1,000 inside the box, right? And you all verified that you've got uniform distribution in your box, and your box is half by half by 0.01. Yes? Okay. So now I'm going to hit save. You should hit save right now. In case something blows up, we can come back. And now I'm going to clear my, I'm going to go into run simulation, clear my previous run, and I'm going to hit run. Also make sure your time step is 1e minus 8. Yep. Okay, export and run. And now it takes a little bit longer to run, but it's not horrible. Done. And now hit reload viz. And I'm at this point in time. I'm going to go back to time 0 and hit play. And you should see something like this. So this is a version of a non-stationary Turing pattern, right? And in Turing's classic paper on Turing patterns, most of the paper deals with the stationary type that describe spots and stripes on zebras and leopards, or vice versa. And that's talked about a lot. But he also has this brilliant section on non-stationary Turing patterns. He doesn't mention Lotka-Volterra specifically as a mechanism. He's got some other equations for non-stationary Turing patterns. But in the later literature, you don't hear it talked about very much, the non-stationary type of patterns. The stationary ones have been of more interest to morphologists who study development of stable patterns in biology, like how come we have 5 fingers and 5 toes, and why do our bodies have bilateral symmetry and things like this. These are all examples of these kinds of patterns.
Except, I don't know, I'm not so sure.
You're not so.
They're stationary.
Yeah, exactly. This is it, right? So in mathematical modeling, danger is thinking the equations you're working with are describing reality, right? And they describe something, but do they describe reality? So this is the danger, but also the challenge and the burden upon us as computational cell modelers is to basically follow the advice of Einstein, who said, or paraphrased, who said, models should be as simple as necessary, but not simpler. Finding out where that knife edge of necessary is, that's the hard part, right? And by necessary, he meant necessary to reflect reality, right? Not necessary to serve some artificial need that you think you have. One of the dangers is to become like the drunken man who's searching for his keys under the streetlight because that's where the light is. Well, wouldn't it be convenient if the keys were there? But what if they're not? Okay, so looks great. So before lunch, we're going to make one little tweak to the model. Oh, well, so okay, so we didn't do the most important thing. So, well, this is important. We're visualizing our thing. Let's hit pause. Now let's go to our plot output settings. What's the graph look like for this crazy thing? So we get a chaotic oscillator. It still oscillates on the global scale. So this is the count of the particles in the whole world, right? So we get ups and downs in the global population, but what you don't see in this is the local pockets and the dynamics happening in those local pockets. But somehow those dynamics tend to be synchronized even across the whole population to produce these global peaks and valleys in the whole population. Okay, this is the diffusion limited version of La Covaltera. Diffusion limited meaning that diffusion is slow enough relative to the reactions that it puts a limit or has some impact on the dynamics of the system. We're now going to change the parameters a little bit and implement a reaction limited version, which will be closer to the classic ODE system of ODE's version of what goes on. Okay, so before we do that, I'm going to do a save as. Well, do a last save to make sure you've saved. And now I'm going to do a save as, and I'm going to change the name to LV underscore reaction limited. And it can be in the same directory because we're changing. Yeah. Save as blend file. And so now we're going to be making some changes to the parameters, but it'll be in a new version of the model named LV reaction limited.blend. So we're going to first change our reaction rate constants. So for the prey breeding reaction, or reproduction reaction, prey goes to prey plus prey. That rate constant, we're going to change it from 8.6 E6 to 1.29 E5. So to go from diffusion limited, where the reactions are faster than diffusion, and diffusion is slower than the reaction, so diffusion has a major impact on the dynamics. We're going to make the reaction slower to bring it more down, to make it be slower than diffusion, and so that now the reactions are having most of the impact on the dynamics, and diffusion is going to be fast relative to the reactions. Okay, and what fast and slow means depends on, with respect to the dynamics that's happening, right? And there's a whole, we could go into a whole, discussion for the rest of the whole workshop on of this system as a dynamical system to explore all that. We're just using it here as an example for a fun thing that you can do to get you started with these tools. Okay, so 1.29 E5, so we made that slower. The next one we're going to look at is the predation reaction. Predator plus prey goes to predator plus predator. We're going to slow that down from 1 E12 to 1 E8. Okay, and then finally the predator death rate. We're going to slow that down from 5E6 to 1.3 E5. So we slowed it down, but they're still dying out a little bit faster than the prey, or it's a little bit slower than the prey breeding rate, right? And that difference is important. Okay, so 1.3 E5 for the predator death rate. And then the last change we're going to make, since we slowed all that down, the dynamics of the whole system is going to be on a slower time scale because we're not changing diffusion. Diffusion is going to be on its time scale that we're leaving alone. But because the dynamics of the reactions is slower, we can, the time evolution of the whole system is going to be slower. So we're going to need to slow down the time step. We don't have to be at quite as fast of a time step. So we're going to make the time step be 1e minus 6. Oh, so 1e minus 6. 1e minus 6. There we go, 1e minus 6. And we're still going to run for 1,000 iterations. So the total amount of time that we simulate is going to be 100 times longer because we made the time step 100 times coarser, right? OK, so now we're ready to run, I believe, yeah.
If we don't clear, how can we handle the different runs that we have?
What's that?
If we don't clear, how can we analyze the different runs that we have?
Oh, so, if you want to, there's a way to keep your previous runs.
Like you can compare the diffusion limited against the reaction limited.
Right. Well, they're in two different directories. So when we click on clear runs, all that's doing is it's clearing out the log files that were generated for the runs. The results of the runs don't get erased when you do that. That button only clears out the table and logs of the previous runs, but not their results. So, and because this is a file with a new name, the results of the other one are still in that location. So we'll still be able to do a comparison.
But if you were to just change the parameters slightly, and then you had a table of these are the different results.
There are ways to do that. We're going to cover that later, but not right this instant. And you can do with these tools, you can do parameter sweeps on compute clusters, and have the runs automatically distributed across the compute cluster, all from the comfort of your chair. Okay, so I'm going to hit run, and it's going to take a little bit longer to run, like a lot longer to run. Why is that taking so much longer? Oh, and slower. Okay. Okay, I think I know the problem. So we're going to do an optimization that will make it run faster. Before we wait for the output, we could wait, and it'll take a while. So this is where sometimes runs take longer than you expect, and you think, oh, something went wrong. So we have a convenient way to kill it. You could just say kill all simulations if you have more than one going, or kill selected, and it'll die. And then the icon here changes to an X that tells you that it didn't really complete. You'd get a green check mark if it completed successfully. This means something wrong happened. Well, we killed it.
Did we forget to change one of the reactions? Because I think 1E8 for the value of the predation. Right?
Yeah, so the predation rate should be 1E8. Okay. You should have changed that, yeah. So there's another setting that is a runtime optimization setting that's really important to learn about, and it's the partition setting. So right now, if you click on the partitions setting, it doesn't say include partitions. So MCell will choose default partitions, which aren't really so good for this situation. So partitions are divide and conquer optimization, where MCell chops up the world into little cuboids, and that makes it faster to figure out who's colliding with who. And the default settings aren't so good for this model. So if you go under include partitions and then say automatically generate boundaries, you'll get some settings. and we're going to optimize this a little bit further. So the X and Y partitions are OK, but the Z one we need to tweak just a little bit more. So we're going to change the Z start to minus 0.007.
How would you know how to do this?
The way I'll explain I'll explain in 1 second. We can do that while it's running. I'll explain it while it's running, and then the Z end plus 0.007. So first of all, and then for the Z step 0.014. Okay, so our box is 0.5 by 0.5 by 0.01. And you saw that the settings went from minus 0.25 to plus 0.25, so that's the limit of our box dimension. And then it's making little cuboids that are 50 nanometers on a side.
Mine says 20 for some people.
Yeah.
Oh.
Then I pressed the arrow next to it and it went to 50.
Oh, 20 might be better. 0.02. 0.02. I'm not sure why mine said 0.5. Not sure why.
I did.
Okay.
Automatically.
Yeah.
Yeah.
Yeah. Not sure why mine said that. Because you were watching, I didn't change it. Not sure why. And then this one went from, and the height of our box is 0.01. So this automatically chose to put this Z start and Z end at the limits of that. But generally, you want to chop up your space so that your partitions are just a little bit outside. For X and Y, it didn't matter, but for Z, it's going to matter more because most of our surface lies in the XY plane, but at two different, basically, perpendicular to the Z-axis, right? So changing the Z-axis is going to move the position of these XY partitions, right? And so we've made it just a little bit outside of that. And that helps the ray tracing algorithm that MCell uses to figure out who's colliding with who. Minimizes the number of particles in each cuboid so that the number of particles that have to be checked for collisions is a minimal number. But you don't want your partitions too small because the diffusing particles have to move from one partition to the next. Those partitions themselves are a boundary that we have to check whether we cross, right? So there's a sweet spot in tuning this. And the defaults are usually pretty good. But this is a special case where the height of the box is so thin that we want to make sure we're just a little bit outside of that.
And partition crossing is checked at every time step?
Yeah. Yeah. Maybe even multiple times per time step if the partitions are really close together and a particle is moving really far. It has to march from one partition to the next as it diffuses. OK, so now we're ready to run again. I hit save, and I'm going to say export and run. And it's still taking a while to run, but it's faster. It's noticeably faster. Oh, and if you look at your terminal window, you can see how fast MCell's running. It tells you how many iterations per second it's doing over here as it goes. So in part of this tuning of the partitions process, you're looking for the sweet spot to find the fastest runtime. You can do that by looking at how many iterations per second you're getting. Oh, Jacob and Bob, a fun thing to do might be to say 90% complete, but also maybe put iterations per second in there. That might be useful. Cool. OK, so mine finished.
Ours are slower.
OK.
Mine finished, but it actually doesn't, I don't see anything anymore. It's like pause on the previous. Reload viz.
Oh, you have to say reload viz.
Okay.
Yeah. So you often have to reload the viz between.
Wow, they're busy.
So you should see something like this that oscillates between green and red globally.
Yeah, wow.
So you don't get patterns, or if there are patterns, they're on a much finer time scale, space scale. And you see the entire volume oscillating together. So even though the interactions between the particles are all local, between one particle and another, somehow there's global synchronization across the entire population, which is kind of cool to think about. And if I do my plot output settings and plot it, we see this.
And this is the classical solution.
And this is the classic local Volterra, except you see that it's not a completely regular oscillation. There's still some diffusion consequences, or some diffusion component of what's going on. But it's much closer to the purely reaction limited regime.
So would that converge if we increase diffusion speed like way higher?
Yeah.
So I don't know if I have a different seed. I have
Yeah.
a similar looking plot, but it's clearly not the same data you have there. I
Yeah,
don't know if I
mine-
changed
mine
the
is
seed
different.
somewhere.
Huh.
Different than hers.
Yours
Could
is
be
the same.
Could be some small. difference in
So,
setting.
so,
Yeah.
so Jacob may have made.
The bundles might be, yeah, I think they're using a different branch because I wanted to make sure that they, yeah, because were you
I'm using master.
Yeah, I think I might have been
Who's
using.
using a different?
So you all are using a different branch of the MCell code.
This is like
Sounds
yours.
much, yeah.
Oh.
I think yours and mine are.
Yeah.
Weird. Oh, that doesn't make sense. You're all running the same seed?
So if
Plot.
Dunno.
Where does it say the seed?
Can you plot it again?
Hers matches the one on the end.
Yeah.
Oh, weird.
They may have a.
if there's a
The input if their input parameters are
if
slightly
if
different.
there's a tiny decimal point
Yeah,
change.
that's what it do it.
What if they ordered the molecules differently or things differently?
Ah,
It is.
yeah,
Yeah.
yeah. If your release site 1 is prey instead of predator, or
Yeah.
vice versa, that will change, right?
Yeah.
So
I just happened to do it that way.
yeah, yep.
Okay.
that would be it. So so the models. So this is a good a teachable moment. This is a good teachable moment. So these are stochastic simulations that we're doing, that are because they're stochastic and because they're done on a computer. So I think it was John von Neumann who worked, was one of the founding fathers of modern mathematics for dynamical systems and lots of other things, and Monte Carlo simulation. So together, John von Neumann and Ulam invented the first Monte Carlo numerical method that was used during the Manhattan Project to figure out what the critical mass was to get runaway neutron breeding in the critical mass of uranium, so that you can get an explosion. If it builds up fast enough, if the neutron runaway builds up faster than the thing falls apart because of the heat, then you'll get to super high order and get a really huge explosion, right? So it's the difference between a fizzle, what's called a fizzle, and super high order reaction. To figure that out, there were no numerical methods at the time that could do it except for Monte Carlo integration of the equations. They were really hard equations to integrate. But to do that, you need random numbers. And on the computers at the time consisted of a room of people called computers who computed on adding machines. And they had tables of numbers. And one of the tables was a table of random numbers. And the random numbers were created by sampling radio waves from the background. They didn't know about the cosmic background radiation yet. This was radiation from the sun, and the Van Allen belts and everything make these radio waves that you could then sample and get random numbers. And someone did that, and that was another person's job, was to make these tables of random numbers. But then later, toward the end of things, they started to have pseudo-random number generators on a computer. And this is where I was going with the story. As von Neumann said, that was the most absurd thing he'd ever heard of, to use a computer to generate random numbers, a deterministic equation. I think he called it not absurd. I think he called it like an asinine, or something like that, an asinine thing to do. But this is what we're doing, right? And so we have a deterministic equation that is generating our random numbers. So if we use the same seed, we get the same stream of random numbers. The generator that we're using is a really, really good one. It's called the Isaac 64 random number generator. You can look on Wikipedia for the Isaac, ISAAC, and it's an acronym. And it's probably the best random number generator in the world. You may have heard of one called the Mersenne Twister, which is a pretty good one, but the Isaac generator is even better. There's lots and lots of people who use the Mersenne Twister, and they think it's the greatest thing. But Isaac is, if you read the Wikipedia page on Isaac, it's understated what it can do. It's way faster than the Mersenne Twister. It's way more random, more random, right? Random in higher dimensional space, right? So at some point in some high dimensional space, there's a pattern. The space that Isaac lives in has a repeat sequence that's like 2 to the 20,000 long or something. So you'd have to generate 2 to the 20,000 and something random numbers before it would repeat the same sequence again. Doesn't mean it's not going to repeat the same number somewhere along the way, but then the next number won't be the same as it was last time. You have to go 2 to the 20,000 before you get to repeat. And it can generate about, on my laptop, I think like 500 million random numbers a second. It's a ridiculously huge number of random numbers. And it's cryptographic quality, which means there's no discernible pattern in it, and it's been proven mathematically that the only way to deduce the pattern of it is to collect a huge number of random numbers in a sequence. And that's the only, and the number that you need to pull out before you can deduce what the parameters are in the sequence is some number that's so big that there's this cryptographers have this concept of a infinitely powerful computer that has a mathematical definition, and if it takes this theoretically impossible to build computer that is so big that it would take up most of the mass of the universe, right? Some computer that's that big, so that you're safe with this for a long time to come, even with alien technology, right? That it would take a computer that big, more than the age of the universe, to figure out what the sequence is. That if you have a generator that's that good, it's called cryptographic quality. So this one satisfies. So you can be sure, but if you run the same exact setting again and again and again, you'll get the exact same result. So we get actually a pretty good thing where we got a pretty good random number generator, but we can repeat experiments and do it again and see what, this is really important for numerical simulations because you want to see if you can repeat the same result again and get the exact same result in case there was a bug and you can figure out what went wrong, right? If it did something different every time, how would you know you're getting, the right answer, right? So, but it's very sensitive. Stochastic simulations are very sensitive to the order in which you do things. So we get the sequence of numbers that's repeatable if I have the same seed, but and those numbers are read out by MCell as the simulation proceeds. And each time, and for each number in the sequence, MCell decides to do something with that number, right? If I change the order in which the numbers are read, or if I change the order of what I do with the number, right? Like in one case, I'm making prey, in the other case, I'm making predator in a different order, right? Then those numbers are the same sequence of numbers, but they're applied to a different species in the system, and so you're going to get a different result.
Which could be one way to check your model, to make sure it's actually giving you a legit value.
Right.
If it gives you a value no matter what seed or what.
Yeah, exactly. And the other thing that you're guaranteed to do is, since these are another thing about stochastic simulations is you can run multiple simulations with different seeds of the same system and see that it converges to a mean behavior that is sensible, right? But with an ODE or PDE, you would get the mean behavior directly, but that's all you would get. You wouldn't get the variance and kurtosis and higher order moments of the dynamics of the system. And those are things that you get with a stochastic simulation. Another thing you get is things that can only happen in stochastic simulations, which are behaviors that aren't on a continuous number line, they're on a discrete number line. And you get very different kinds of behaviors where you can't have 0.1 prey molecules, right? You can only have 0 or 1, right? And when you have a system that behaves that way, the dynamics of it can be actually qualitatively different, not just quantitatively different, but actually qualitatively different kind of behavior will emerge from that. So with stochastic simulations, you'll be able to see things and observe things that you wouldn't be able to observe with a continuum approach. So before we break for lunch, I think it's probably time for the lunch break. Does anyone have any questions?
Yeah,
Yeah.
I'm just having trouble understanding why it's called a stochastic simulation when we're all running the same simulation and getting the same result. So, like.
So okay. So let's just to demonstrate that. Let's switch back. I think it'll be more clear if we switch back to the diffusion limited one.
Because I paused mine at the exact same time point as yours, and I see the same exact.
Yeah, it's because we're all using the same seed. In the.
But even that, so wouldn't that be deterministic?
Well, this is where von Neumann said it's absurd, right? So we're using, these are random numbers, but they're deterministically created random numbers, right?
Yeah. So this, okay. So
right.
The randomness is coming from the seed.
From the seed and the sequence of numbers that's being generated.
Is literally this sequence of random numbers.
Yeah. The seed is used to as one of the parameters in the equation that creates the random numbers.
Okay.
It would be like your crypto key.
So like every.
This is like the cryptography key. So the relationship between cryptography and encrypting information and random number generation, that relationship is like this, right? It's the same thing.
And so every random walk uses the same seed.
Yeah.
Okay.
Well, the whole simulation is using a sequence of numbers and using it for different things. Each particle is not it does not have the same random walk.
Right.
Right? But globally, the whole system is all doing the same thing if we use the same seed. The same exact system.
Can we ask it for a random seed?
Yeah.
then you just be sampling from the same set of random numbers to generate the random number that would then generate a random number.
That sounds like a logical thing to do, but actually, it's actually easier to figure out the sequence if you do things like that. If you're using that to generate a sequence. So what we do is, well, we'll just stay in this simulation, the reaction limited one. I'm going to plot my plot and leave, and then instead of making that go away, I'm just going to leave that up. I'm going to leave that up, and then back over here in my run simulation, I'm going to clear the completed run, and under under output control options, this is where you can choose a different seed or a range of seeds that will each run concurrently on as many number of processors as you want. But what we're going to do is I'm just going to put in seed number 2. So it's going to go from 2 to 2. And now when I hit export and run, it's going to run with seed number 2. So I'm going to click that and go. And I think there's a way to superimpose these plots, but we're just going to plot them in separate windows and look at them side by side. Yeah.
Supreme Court just lifted the stay on the travel ban.
Say what?
Supreme Court just lifted the stay on the travel ban.
Oh no.
I don't know what kind of country I live in. What
Yeah.
does it mean? Sorry.
I didn't think that was going to happen.
Lifting the stay.
So where's the run number 12 under the MC indicator?
It's a safety margin. If you
I know the run
put in
number
a huge
is
number, it would overrun your computing resources. It makes you make that number that limit. And the reason that is we actually have parameter sweeps where you can say, okay, I want to sweep the number that I'm going to release from 1 to 10 by steps of 2. Oh, and I'm going to sweep my diffusion constant in this molecule from this to this. And before you know it, you've got like 5 dimensions with 10 samples each, and you've got a million runs. And so that's kind of like a safety check to keep you from running more runs than you want.
I almost said -1 doesn't it fall?
Yeah,
-1 means no checks.
So if I take my 2 plots and I kind of stack them one above the other, you can see they're doing very different things. So, similar but very different, right? Similar in character but different in detail. And if we use the diffusion limited one, which was much more chaotic, you would see much more dramatic change. Yeah. 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 There's is there a way to save the model? So we're using this within the GUI, right? But what if you were running on a supercomputer, right? So I think after lunch we'll show you more about the where the files are stored. So MCell has so this is the GUI interface to model building, which is oftentimes a GUI is the right tool for the job, but sometimes a text editor and a bunch of files is the right tool. So when we hit the export and run button, what's happening there is the internal representation of the model in the GUI is being written out as files that are in the MCell model description language format in a certain directory. And those model description language files are a whole other language that describe the model. And there's a quick reference guide to the syntax of that language. But those files are what MCell really uses to do the runs. And they're written in human readable form. They're not in XML form. They're nicely formatted. And there's even some comments and stuff in there. And those are meant to be edited by hand if you want to. There's also a Pythonic interface to MCell where you can make models in Python. And the Pythonic interface is something that's new and under development and changing, but we'll also have, I think tomorrow afternoon, we have time set aside to talk about the Pythonic interface. But the files that are written out are in a well constructed layout that are meant to be made into a tarball and shipped over to a supercomputing resource where you could run MCell on a queuing system, this kind of thing.
There's also a scripting capability built into Cell Blender where you can actually script the model using Python directly as well.
Yeah, all in this interface. So over time, the interface and its capabilities have grown so much that in a 3-day workshop, or even in our 1 day that we have devoted to teaching you about this, there isn't enough time to really go into it except to just mention it and touch upon it. But our team is available to and eager to help you with your individual projects, here and after the workshop is over. As you continue to use and grow and learn the tools more, we're here at your disposal to help you in any way that you want. Because there just really isn't enough time during a 3-day workshop to do nothing more than mention it, show you a few things, and mention it and answer your question. Yes, you can do that. Yes, you can do that. And the answer is often yes. Very, very rarely no. Or we scratch our head saying no. Oh, actually yes. So it's kind of like that. So any other questions right now before lunch?